Yes. Good morning, everyone. I'm glad to present our recent research work. The title of my presentation is Engineering the Photoelectronic Properties of Oxide Materials. My name is Shusheng Pan. I come from Guangzhou University. First, I will introduce some background. Second, I will present some UV photo detection materials, tin oxide and chromium oxide. The third, I will introduce some solar absorption materials, amorphous titanium oxide. And at last, I will give some summary. It is well known that the oxide materials is abundant in the earth, and they have many important properties such as magnetic, nonlinear optics, superconduction, and laser superconduction, and piezoelectricity. And some oxide, such as silicon oxide, ITU, YBCU, and NDYAG have been widely used. First, I'd like to introduce some content about UV photodetectors. The UV photodetectors have wide application in civil, industrial, and military field, such as missile warning, UV astronomy, security, communication, and high voltage corona detection, and some flame remote sensing. For an ideal photodetector, the figure of merits include appropriate response wavelength range, high external quantum efficiency, and high responsivity and high detectivity, and no NEP, no dark current, and short response time. However, current UV photodetector still has no detectivity. In fact, the UV photodetectors require high detectivity because the absorption or scattering of UV light by gas molecular and aerosol in atmosphere. I will introduce some intermediate band semiconductors. For the solar cells application, the intermediate band is partially occupied, and the optical transition between intermediate band and conduction band or valence band will expand the optical absorption range. For UV photodetectors, the intermediate band is fully occupied, which can reserve and release the electrons. The electrons generated by the defects can be reserved in the intermediate band. As a result, the dark current is low. Under UV light illumination, the electrons can be excited from valence band to conduction band, leave holes behind, and the electron jump from the intermediate band to valence band, and then those new electrons were excited to conduction band to supply photocurrent. Thus, the photoconductor has high photocurrent. Furthermore, the optical transition between conduction band and the intermediate band is forbidden, which reduces the visible light response. UV photodetectors require visible light blind or solar blind. The tin oxide is special, unlike antimony, phosphorus, and arsenic. The bismuth doping will generate an intermediate band with high density of state within band gap of tin oxide. This is the theoretical calculation. The bismuth doped tin oxide. We have prepared the bismuth doped tin oxide by magnetic sputtering, and the bismuth doped tin oxide is high transparency in UV, invisible, and NIR, near infrared light range, and the band gap nearly unmoved. From the XPS results, the bismuth have two oxidation states, +5 and +3, and the +5 bismuth is dominant in the BTU films. This is XPS valence band spectra. From this spectra, one can see there is extra electrostate located around 1.8 eV below Fermi level in BTU, which comes from intermediate band states. This is the band structures from the optical band gap and the XPS valence band spectra. The BTU films, bismuth doped tin oxide films, have strong absorption in the UV light range, and the absorption in the visible light is very weak. And we have fabricated the BTU photoconductors. The gold films is deposited onto the films, which act as the electrode. The dark current of our photoconductor is very low, is about 0.25 nanoampere at 1 voltage bias. This is the responsivity changed with wavelengths, and the maximum responsivity of BTU film photodetector is about 16 ampere per watt at 280 nanometer. The width of the responsivity is about 40 nanometer. And the responsivity is very low in the visible light range, which indicate the BTU is visible light blind. And the detectivity is very high than 10 or 14th power joules at the UV wavelength range from 220 to 380 nanometer, with maximum value of 6 multiplied by 10 or 15th power at 280 nanometer. And we compared with the BTU photodetectors and other materials. And the BTU films have no dark current density, high responsivity, and very high detectivity. Furthermore, the wide dynamic range of 195 dB indicate the BTU can not only detect weak light, but also probe the intense light. The second photodetector materials is nickel-doped chromium oxide films. The nickel-doped chromium oxide have been deposited on sapphire by pulse laser deposition, and the films are 001 oriented. The optical band gap changed from 2.9 to 3.1 EV are combined with enhanced UV absorption. The dark current of chromium oxide is greatly enhanced after nickel doping, and the films present evident photo response in UV light. And this is a responsivity changed with wavelengths, and the responsivity is enhanced more than 100 times from 1064 to 365 nanometer after nickel doping. The responsivity of nickel-doped chromium oxide is 116 microampere per watt at 365 nanometer, and the undoped one is about 0.357 microampere per watt, and the rise and 4 times of nickel-doped chromium oxide are 9.5 seconds to 9.8 seconds. The third part of my presentation is about solar absorption materials, amorphous titanium oxide. It is well known that titanium oxide is widely used in photocatalysis and solar cells, and titanium oxide is called solid materials. However, due to its wide band gap, the titanium oxide has weak absorption in invisible light range. In this study, we have prepared amorphous titanium oxide by pulse laser ablation in water, and we use 355 nanometer UV laser to irradiate the pristine titanium oxide. And the color of titanium oxide is changed from white to blue. This is the TM results. The titanium oxide is amorphous, and this is optical absorption of titanium oxide. And from the optical absorption, the amorphous titanium oxide has ultra-wide absorption from UV to visible to near infrared light, and the amorphous titanium oxide band gap is fixed. From the XPS valence band spectra, one can see there is existence of intermediate band electronic states within the band gap. As compared with this one, the pristine titanium oxide, the band gap emission band to band recombination, the pure intensity is greatly enhanced. And furthermore, there are some intermediate band related emission from the pure results. And furthermore, the intermediate band related photoluminescence has non-pure decay time. It's about 710 nanosecond. Okay, some conclusions. High performance UV photodetectors have been achieved in tin oxide and chromium oxide. Wide band optical absorption have been observed in amorphous titanium oxide through pulse laser ablation in water process. The last, engineering the intermediate band within band gap of oxides semiconductor can even evidently enhance their photoelectronic properties. Okay, I'm glad to thank the supporting National Natural Science Foundations of China and Home Scholar Program and the China Postdoctoral Science Foundation. Thank you for your attention.